Okay, so you can see this, the slide, right? Okay, so so today we will do a tutorial, some example exercise concerning Turbojet and Turbofan. Okay, so I have recorded, I have shared with you the video. Okay, this one, right? These slides. Okay, about this chapter, Turbojet and Turbofan engine. Okay, so okay, the single spool turbojet, two spool turbojet, the thermodynamic analysis. Okay, this is the most important part. So we are going to do exercise tutorial on this thermodynamic analysis. Okay, ideal case. And then, okay, this is the process, the explanation of the process throughout the cycle. Okay, so it is like a Brighton cycle. If you remember Brighton cycle in aerothermodynamics, the gas power plant, gas turbine power plant cycle, right? In aerothermodynamics, you have learned a lot of thermodynamic cycles, like Carnot cycle, heat engine, etc. So the cycle that we are going to apply for propulsion engine, jet propulsion engine, is Brighton cycle. So it is like a gas turbine cycle, the power plant cycle. Okay, so the difference is that gas turbine cycle for power plant is a closed cycle, a closed system, closed cycle. So you have like a kind of the ideal case like a rectangular, something like that. Okay, so you have a closed cycle from the initial point, and then after you complete the compression, combustion, expansion, condensation, so you will return to the initial point. Okay, and the cycle will repeat. Okay, that is closed cycle. Okay, thermodynamic closed system. Okay, so that is for gas turbine power plant in industry, at the factory. Okay, but for jet engine, is the same cycle. I mean, it is still a Brighton cycle, but Brighton cycle with open, we call it open system, open cycle. Okay, so for jet engine, it is an open cycle. So what do you mean by open? Is that, okay, so we first have the general. Okay, I just explain the general cycle. We first have compression, and then we have a combustion, and then expansion, and then the fluid, the air, is supposed to be rejected to the environment, ambient. Okay, there is no condensation. Okay, if you remember the thermodynamic cycle, compression, and then combustion or a boiler. For power plant, we don't have a combustion chamber. We don't use combustion chamber for power plant. The heating process, we call it evaporation. So we use a boiler, right? Evaporation to heat the fluid. Okay, that is for power plant. Okay, but for jet engine is an air gas. So we use the heating process is actually occur in the combustion chamber. Okay, but the graph, the cycle is the same. It's just that the process, okay, and the material, okay, we use is different. Okay, for power plant is boiler or evaporation, but for jet engine we call it as combustion chamber. Okay, and then the fluid is heated up, and then we have expansion in a turbine. So that is the same expansion. And then the heat for power plant will be condensed back. Okay, but for jet engine there is no condenser. Okay, so the fluid, the air, after being expanded, it will goes into nozzle. Okay, to produce high speed velocity of the air, and then the air is and then we produce the propulsion. Okay, propulsive force. Okay, and the rest, the extra air will be rejected to the ambient. So that is why it is called open cycle. Okay, so you have to understand the process. Okay, this is more detail. We have compression as heated in the combustion. Okay, mixing the fuel and the air, expansion, and then if we have afterburner, means that we burn it one more time, means another combustion chamber, another burner. Okay. adding to the to heat again the air, and then the air exit, okay, accelerated, exhausted through the exhaust nozzle. Okay, that is the ideal process. So ideal case, reversible adiabatic, which is we call it isentropic or reversible adiabatic. So this one you have learned in aerothermal. Okay. Okay, so we generally explain it in TS diagram. Okay, we sketch the cycle, the thermodynamic cycle in a TS diagram, temperature versus entropy. Okay. Okay, temperature versus entropy. So this is the thermodynamic ideal case diagram. So we have at intake air, we call it point A at the environment A, and then we have okay, actually we have diffuser between A and 1. There is a diffuser. So the function of the diffuser, I've explained. The diffuser is opposite of the nozzle. I mean, the function is opposite to the nozzle. Means that we want to decelerate, okay, to slow down the air, the velocity of the air. If for nozzle, we want to speed up, okay, the velocity of the air. Okay, so A to 1, location 1, which is in TS diagram, it is the same point temperature and pressure. So that's why you can't see the point 1, because the temperature and pressure is assumed the same or practically more or less the same, okay, at point A and 1 and 2. So 2 to 3 is the compression, okay, compressor, and 3 to 4 is the combustion chamber, 4 to 5 is the first expansion in the turbine. And then if we have afterburner, okay, if the afterburner is functioning, so we will burn it one more time, another burner, another combustion chamber, one more time, heat up to temperature 6A. Otherwise, we will directly from 5 to 7 nozzle, exhaust nozzle. Okay, if we have afterburner, then 6A to 7A, from 6A to 7A. This is nozzle. This is also nozzle. Depends if we have afterburner or not. Okay. And then, okay, last one, 7A. Okay, actually this is should be drawn like a dot yes, because the cycle is open. It's not a closed cycle. Okay, so 7A, from 7A, the air, the fluid in the engine will be rejected to the ambient environment. So this is the ideal turbojet TS diagram. Okay, you have to remember the okay, even though our exam or test is open book, but at least if you remember, okay, if you can imagine in your head, the cycle is more easier for you to when you want to do exercise tutorial, because you understand the process, whether the temperature is increasing or decreasing, right? Okay, so it's better if you can remember, okay, this TS diagram. At least you have the idea, okay? You know when is the temperature and pressure will go increase or not, okay? If you remember also this one, okay, this line in TS diagram, this is the isobar line. Isobar means the pressure is constant, okay? So in ideal case, we suppose that the combustion process occurred during constant pressure. Okay, when we burn, we mix the fuel and the air. We assume in ideal case that the pressure is constant. So this is isobar line in TS diagram. Okay, so this is isobar line. So we assume the process is constant, pressure constant pressure. Okay, but in real case, of course, the pressure will be modified a bit, okay, will be different, will change a bit during the combustion process. You will lose a bit the pressure, okay. So this is the process, okay. Okay, so actually I just paste this equation, okay. I know that it's a bit blur sometimes, okay, but we will use this all of this equation of the cycles today, okay. So I just paste them here so that you have the equation, okay, but we will do the exercise, okay, so that you will understand better, okay. Okay, so this is actually all the thermodynamic equation, okay, from point A, point 1 to exit point 7, okay, nozzle. So basically, when we want to evaluate the performance of the turbojet engine, okay, if we were asked to do evaluate the performance of the turbojet engine. So when we mention performance, it means that whether we have to calculate the thrust force, or we have to calculate the TSFC, thrust specific fuel consumption, or we have to calculate the propulsive efficiency. Normally it's that, okay? Those parameters, okay, that we have learned in previous chapter. So if we want to evaluate the performance of an engine, turbojet or turbofan engine, so we have to calculate these parameters, these performance parameters. In order to calculate these performance parameters, normally we have to, even though the question did not ask you, but normally you have to start start from the initial point, which is at the point 1 diffuser or compression before intake pump, okay, before intake compressor, okay. So so we have to calculate at each point from point 1, 2, 3 thermodynamic cycle just now. So we have to calculate all the physical value, which is normally temperature and pressure, okay. In the end, in order for you to get at the end the thrust force or the propulsive efficiency, okay. So that's why all these equations are given. Tadi ada yang nak masuk saya tak sempat accept, okay. So that's why all these equations are given, because you have to calculate from point 1 the pressure, the temperature, okay. So and then etc. So until point 7, until exit at the nozzle, and then when you have all these values, you have because the temperature and pressure at, for example, at point 3 depends on the temperature and pressure at point intake 2, intake compressor. So and so on, so on, so on. So you have to start from the beginning, and then from 2 to 3 to 4, you cannot calculate directly point 7, okay, because you need from the point 7 needs point 6, and then etc. Okay, previous. Okay, so so that's why all these equations are given here, okay, because there is step by step to do. And at last one, we will calculate the thrust force. Okay, this is the same equation in previous chapter. Okay. Okay, this one. Okay, and then I have shown you the turbofan engine. Okay, so the same as in turbofan. You have, okay, this point cycles. Okay, so the thermodynamic, the TS diagram. Okay, okay, TS diagram for turbofan engine is slightly different from the one of turbojet. So here for turbofan, okay, this is the TS diagram for turbofan. So we have, okay, A at the intake, and then 2.2, okay, from A to directly point 2 at the diffuser, okay, outlet of the diffuser, and then 2 to 6, okay. Okay, so this is the schematic diagram. Okay, 2 to 6 saya pun tak nampak sangat. Okay, okay, because of the fan we have two airflow, the bypass airflow and the core engine, right? Remember the cold air and the hot air, or the core engine and the fan at the core duct and the fan duct, okay? So that's why, okay, from this point 6, I think, okay, 6 is actually, no, point 8, sorry, okay, point 8, 8 is actually at the bypass duct, okay, at the bypass duct from 8 to 9, okay, exit, okay, 8 to 9, this one, 8 and 9. So this is the bypass, and this is the core engine. Okay, this is schematic diagram, core engine flow, and this is the bypass duct flow, bypass air flow, or this is one is the primary or core engine flow. So 8 to 9 is this one. So is a bit different, okay? And then this 2 to 3 is the compressor, so the same as turbojet engine. And then 3 to 4 combustion chamber, 4 to 5 a turbine, 5 and 6, okay? 5 and 6 depends if you have afterburner or not. And then 6 to 7 the exhaust nozzle, okay? Okay, so these are the thermodynamic equation for turbofan. So it's a bit for turbofan, it's a bit longer, a bit more complicated, of course, because we have two airflow. Okay, the bypass and the primary, which is the core engine. So the equation is more longer. Okay, so until we reach the TSFC and the thrust equation. Okay, don't worry, you don't have to remember even for test. Okay, even if we have face-to-face exam, I still allow you to bring those notes of equations. Okay, but we are going to do online exam, so open book. Okay, so you don't have to remember, but at least you have to understand. Okay, which equation to use. Okay, now for today. Ada lagi tak yang masuk tadi? Okay, so for today, okay, so we have okay, I have 3 exercises. So 1 and 2 we will do together, inshallah, this morning. And number 3 is your homework. Okay, remember you have homework 10%. Okay, so this one, number 3 is your homework. Okay, I will upload the slides later on. Okay, so we'll do 1 and 2 first. Okay, so turbojet. Okay, we will start with turbojet. So the airplane is a fighter powered by 2 turbojet each rated at 12.12 kilonewton. Okay, so the thrust force is 12.12 kilonewton, around 12,000 newton. Okay, so we have, and then we have cruise velocity. Okay, cruising velocity at 310 meter per second at altitude of 9150 meter. Ambient temperature 240, ambient pressure 32, compressor pressure ratio of 12. Okay, compressor pressure ratio means that the pressure ratio between outlet and inlet is 12. The ratio, okay, means that, for example, if we have 12 12 kali 5. Okay, if we have 60, example, 60 pascals at outlet, and means that at inlet, pressure at inlet compressor is 5. So 65 divided by 5 is 12. Okay, so that is the ratio of the compressor pressure ratio. Okay, TIT is the simplified, okay, notation for turbine inlet temperature. Turbine inlet temperature, okay, means at the exit of the combustion chamber before entering the turbine expansion. For expansion, we have turbine inlet temperature at 1,400 Kelvin, which is the highest maximum temperature that the air reach in the engine. Okay, if we don't have afterburner. If we have afterburner, the afterburner is functioning, then the temperature entering the afterburner is the highest temperature. Otherwise, the temperature entering the turbine is the highest temperature, TIT. Okay, or the point number 4 in the thermodynamic cycle just now. And then we have QR. Okay, QR is the fuel heating value. Remember, in order to calculate thermal efficiency, right? We have learned previous chapter. In order to calculate thermal efficiency, we need the fuel heating value. Fuel heating value is like a specific heat. Okay, you have learned in aerothermodynamics, you need specific heat for each fluid. For example, air, we use 1005, right, joule per kilogram per Kelvin, right? But for fuel here, for jet engine, we characterize the fuel with fuel heating value, which is normally is given around 40,000. Okay, so this one is 42,700 kilojoule per kilogram. Okay. And then we assume ideal operation. Okay, so for your throughout your course, propulsion, we only use ideal case. Okay, later on in elective course, everyday engine, we will see about a real case. Okay, because real case is more complicated. Okay, so this is ideal case, ideal operation. unchoked nozzle. Remember, I've explained unchoked nozzle, choke, unchoke. Okay, this got to do something about this link with Bernoulli principle also. If you some of you have done a thermofluid lab about the Venturi, right? In the Venturi and Bernoulli principle, we have learned something about critical point, right? Critical point, which is that critical point determine the choke, or whether the air, the fluid inside the tube, or this one inside the engine is choke or unchoked. Choke or unchoked means that, okay, when we say choke, the air is choked, means is in other words, it means that the air inside the engine, okay, the air in the flow of the engine is limited. It means that it is limited. When we say that it is choked, it is limited. Okay, in other words, what do you mean by limited? Okay, like I explained one more time. Okay, I have explained this before. Okay, in the previous chapter. Limited means that, okay, means that the mass flow rate cannot be further increased, okay, in the pipe or in the flow of the engine. Normally we try to increase, okay, the air intake, air inside the flow, okay. How we increase the air inside the flow is by decreasing, we kept decreasing the pressure at the back pressure. So the flow will go. If you decrease, remember the Bernoulli principle, Bernoulli, if we decrease pressure, then velocity will increase. Okay, Bernoulli, in the Bernoulli principle. So what we do is that for like a Venturi tube or convergent divergent nozzle, right? We try to kept decreasing the back pressure, the pressure at the end. The back pressure, we kept decreasing it. Okay, so that the velocity will increase. So the fluid will enter the tube, the Venturi tube, or this one in the engine, okay, in the nozzle, okay. The fluid, the air will keep entering the nozzle, okay. The velocity increasing, so, and the mass flow rate also will increase. But until up to some point, which is the critical point, okay, where if we keep increasing the pressure, the back pressure, the fluid, the mass flow rate of the fluid will not increase anymore. Okay, that is the highest point. Okay, the critical point. Okay, where the Mach number is equal to 1. Okay, at the nozzle. Where even though if we decrease the pressure, the mass flow rate of the air will not increase, goes into the flow anymore. So that the point, we call it as at that moment, we call it that the fluid is limited or is choked. Okay, is choked. Okay, so that's what it means. Okay, choke nozzle in the convergent divergent nozzle. Convergent divergent nozzle, or like a Venturi tube. Okay, we the air kept flowing in. Okay, when we reduce the pressure, the air kept flowing in because of the velocity increase, mass flow rate increase. But until up to some point, okay, the air will not be increasing, mass flow rate will not be increasing anymore. That is when we call it choke or limited. The air is limited or choke. So in this one, okay, which is normally in ideal case, we assume that the nozzle is unchoked. Okay, unchoked meaning it is not limited. Okay, it is not limited. It is not limited. Okay. Yeah. Okay, sorry. Anak-anak pun kelas online. Okay, apa tadi? Sorry. Okay, choke nozzle, unchoked nozzle. So for this exercise, the nozzle is unchoked, mean it's not limited. Okay, means that we haven't, the flow haven't achieved the critical point yet. Okay, okay, so when we say unchoked nozzle, means that okay, means that the airflow, okay, if it's choked, then the airflow will not increase anymore, right? But if it's unchoked, means that the airflow still can goes, okay, can flow, okay. So means that the pressure A ambient is equals to the exit pressure. PA equals to PE. Pressure at the exit nozzle is equal to the ambient pressure. Okay. Otherwise, if it's not equal, whether it's higher or lower, then the flow will be choked. Okay. So this one it is unchoked, means that the ambient pressure and the exit nozzle is the same. Okay. Okay. Okay, so and constant CP, we assume constant CP, specific heat for the air, constant CP in our process, which is 1005 joule per kilogram per Kelvin. Okay, so now we have to determine the fuel to air ratio, the F. Okay, the ratio of the mass flow rate of the fuel to the mass flow rate of the air, and the velocity, exhaust gas, the air mass flow rate, and the overall efficiency. Okay. Okay, try to do this one by using the equation, those equation that I have given in the slides before this, okay? So like I've said just now, you have to start with the first point. Even though the question did not ask you to calculate at point 1, 2, but you have to start the calculation, okay, by calculating the temperature and pressure at point 1 and then 2 and then 3, etc. until you reach the fuel to air ratio, which is at the combustion chamber, point 3, between point 3 to point 4. Okay, look at the equation given in the lectures slides. Okay. Wait. Okay. After Raya, after semester break, you have test, okay? So make sure you understand and try to do your homework before the test so that you will understand better. Okay. Okay, so apa dah? Okay, so first, we have to start at the point diffuser, okay, at the intake. So point A, just now in the thermodynamic cycle, you see that the point A, okay, this one, A, okay, okay, we will use this thermodynamic cycle as reference. So we want to calculate point A first, okay? So here the temperature at point A, okay, is the same as the temperature at point 2, okay? Temperature is the same, so we calculate. So if you want to calculate T, we use the total notation, T0, this is total value. So we calculate the total value of temperature and total value of the pressure. Okay, total means that static plus dynamic. Static temperature plus dynamic temperature, so we get the total temperature. Static pressure plus dynamic pressure, so we get the total pressure. Okay, so in Brayton cycle, jet engine cycle, we always calculate the total value. Okay, maybe in aerothermal previously, you only calculate the static value, temperature, pressure. But here in jet engine, we use total value, all total value. So T naught 2, which is also equals to T naught total A. Okay, so how do you calculate this? Okay, so what do we have in the questions? We are given the cruising velocity, means that the flight, the air speed. We are given the air speed at 310, and then we have CP. Okay, the ideal specific heat, the air. Okay, so we, in this case, to calculate T02, okay, we will use the definition of total values, which is total pressure, total temperature in this case. So the definition of total temperature is static temperature plus the dynamic temperature. Okay. So static temperature for ambient is TA, the ambient temperature, plus, remember this one, V square over 2CP. I hope you remember this equation, okay? This is the dynamic temperature plus the TA, okay? So I write it as VF because of the flight speed or air speed given 310. This one, okay. Okay, in this slide, I give you this equation, right, for T naught 2, which is equal to T total A, which is this one, right? But here, in this question, we don't have the value of Mach number, right? Mach number here, we don't know the Mach number. So that's why we use whatever is given, which is V, the flight, the cruise speed, and the specific heat. Okay? Actually, if you remember how to derive this equation, okay, actually this equation is derived from this. Okay? If you change this definition, V, you include the Mach number, the speed of sound, okay, then you will get this equation. This one with Mach number. So this one actually is the same as this one. Okay? It's just that this is how you derive from here, from this definition, static plus dynamic. From here, you change the V at that Mach number, then you'll get this equation given here in the slide. So it's actually the same equation, okay? Except that this one is with Mach number, this one is the initial one, static temperature. Okay? So it's the same equation actually. If you change this one, then you will get this one. Okay? You just change, you use the definition of Mach number, V velocity over speed of sound, gamma RT, you add in here, and you change, etc., and then you get this one. Okay, so it's the same. Okay, so, but here we don't use this one, okay, because we don't have the value of Mach number, so we use the initial definition. Okay, so VF square over 2CP. So, and then you will get the total temperature at point A, and which is the same as total temperature at point 2. Okay, this ambient static pressure temperature is 240. Okay, so please calculate this one. What do we have? Everyone understand or not? Semua faham tak apa saya cakap?
287, Doktor.
Faham, Doktor.
287. Okay, faham kan? Faham kan apa saya cakap? Okay, 287. Okay, it's better if you have some point 8.8 Kelvin. Okay. Okay, so you have the T not 2. Okay, and then calculate. Ada yang baru bangun tidur ke? Okay, and then calculate P total pressure. Okay, at point 2. So look at the equation given okay in the lecture notes. Can we use the equation given? This one, okay. No, sorry, this one, okay. Okay, but it's actually the same definition. Okay, so we P not to between point 2 and point A. Okay, so we use since it is ideal case, so we can use the isentropic ideal gas equation. Okay, this one, like this one. Okay, this is the isentropic ideal gas. Okay, perfect gas, ideal gas equation. Okay, between pressure and temperature. Okay, because we have all the values of temperature, we already have values for temperature, and we want to calculate the pressure, so we use that definition. So, but here we is for point 2 and A, not point 3 yet. Okay, so this is the definition: T A gamma over gamma minus 1. So gamma, whether you want to use 1.4 or 1.33 is okay. If it's not given, if it's given, then use whatever is given. Okay, so remember this equation in thermodynamic, aerothermodynamic. This is isentropic equation for ideal gas. Okay, remember? So you have P total 2 over PA and T total 2 over TA. Okay? Gamma over gamma minus 1. Okay, power of gamma minus 1. Okay, so we do this because we have T total 2 just now 287, TA 240, gamma use 1.4. Okay, 1.4 for here. And then PA ambient is 32 kilopascal, so you can leave it in kilopascal. Then we get PO2. Okay, so what is PO2? Okay, PO2 around 60.4 kilopascal. Okay, so leave it in kilopascal. Is smaller. Okay, the number is smaller. Okay, 60.4 kilopascal. You can leave it in kilopascal or bar, whatever is given. Okay, so this is PO2. Okay, in your homework or your test or final exam later on, after you have achieved, you have calculated all the values, temperature, pressure at all the points from point 1 until point 7. I suggest you, I advise you, is better you tabulate all your values, your answers in a table. Okay, it is better so that I can see your it's better for me to mark, and it's better also for you to verify. Okay, to search back your answers. Okay. So in your homework or your test or your final exam, after you have calculated all the values at each point, you do a table, a nice table, and then you list down all the temperature at all points from point A, 1, if you have point 1, 2, 3, 4, until 7. So it's better for you to look back to verify, okay? So P note 2, 60.4 kilopascal, around that, okay? And then next is 0.3. Okay, for 0.2, okay, semua orang for point untuk at the inlet of the compressor 0.2 Sebab saya nak padam, kita nak buat 0.3 pula. Okay, we want to do 0.3 exit of the compressor. This is 0.2. Okay, so 287 and 60 kilopascal around that lah. Okay, next. Kau apa dah Okay, next. Next for 0.3. Okay, we look at the 0.3. Okay, so 0.3 is the method is the equation is kind of the same. Okay, because the process from point A to point 2 and point 2 to point 3, the process is kind of the same. Okay, this one. You increase the pressure. Okay, so the equation that we use is the same. Okay, so we calculate P3. Okay. So P total 3. Since we have pi C is okay. Pi here is the compressor pressure ratio just now 12, right? Compressor pressure ratio. The compressor pressure ratio is written as is noted as pi. So pi C compressor. Okay, so we use this one because we have the value of the compressor pressure ratio. Okay, so the like I've explained just now, so the pressure ratio is the ratio of the pressure at the outlet over inlet. So outlet is P naught 3, P total 3, and inlet is P total 2. So the ratio. Okay, so this is easy. Just multiply 60 just now. P total 2 is 60 kilopascal, multiply with 12. So you have about 120. 120. 12 ni? Mana lah? Compressor pressure ratio 12. P note 2. Bukan 120. Around 700. Okay, 720. Around 700 12 kali 60. Okay. 725 exactly. Okay. 725 kilopascal. Around that lah. 725. Okay. 12 multiplied with 60 kilopascal just now. 60.4 actually. 60.4 kilopascal multiply with 12. So we have 725. Okay. P total 3. Okay. So this one easy. Okay. Next for T total 3. So we use this one. Okay. Because we have all those value. So this is the same. This is the isentropic equation for ideal gas. Isentropic, ideal but irreversible. Isentropic equation for ideal gas. So this one the same as just now. So T naught 2. Okay. So the this is the compressor pressure ratio. Gamma minus 1 over gamma. Okay. So we have T total 3. Okay, which is around 587.5 Kelvin. Okay, so the same method same method je, sama je method dia. Okay, so sebab tu saya buat cepat-cepat. Okay, so P note 3 725, T note 3 587. Okay, you just use back this equation, this isentropic equation, ideal gas. Okay, everyone?
Yes, Doctor.
Okay. Okay, next. Tak nampak sangat. Okay, next is okay. We will arrive at the point fuel to air ratio. Fuel to air ratio F. Okay. Where is the equation for F? This one. Okay, this is the equation for F. Okay, we assume for ideal case, we assume no pressure drop, means constant pressure just now. So that's why PO3 is equal to PO4, isobar line, the isobar line. This one. Okay, this is isobar line. So we assume ideal case pressure 3 is equal to pressure 4. So this is the equation of heating energy balance, energy balance inlet and outlet of the combustion chamber. Okay, so energy balance mass flow rate times Cp times T, remember energy Q, the heat transfer. So we have mass flow rate times C, Cp, specific heat times temperature, inlet and outlet, okay, plus the fuel heating value. So from this energy balance, we derive the fuel to air ratio. We derive the fuel to air ratio F. Okay, so this is the equation of F. So we will use this one. So F, okay, so that you understand where does this equation for F come from. It comes from the energy balance of the air and fuel inlet and outlet of the combustion chamber. Okay, so inlet you have A, and then we input the fuel, mix the fuel, and then exit the mass flow rate A and F is mixed together. So we have F equation Cp. Okay, here we assume Cp specific heat for air inlet and outlet of the combustion chamber is the same. Okay, otherwise in this equation is written as Cph and Cpc, right? So if we go into more detail, sometimes the specific heat of the air of the fluid after exiting the combustion chamber is slightly different than the before, okay, because we have mixed with fuel. But here we assume that the Cp specific heat before and after the combustion chamber is the same. So I just write it that Cp, okay? Otherwise it's Cpc or Cph, hot and cold, okay? So T04 minus Cp, okay, 3. Okay, Cp T total 4 minus T total 3 over QR, the fuel heating value, minus Cp T 4. 4 exit compressor, air combustion chamber. Okay, so Cp T total 4 minus T total 3 over QR, the fuel heating value, minus Cp T total 4. Okay, this equation is derived from the energy balance. Okay, energy balance, which is the heat transfer, heat exchange, inlet and outlet of the combustion chamber. Okay. Okay. So this one. Okay. So we have Cp 1005 or 1.005 kilojoule. We have T4. T4 is the, as I've explained just now, T4 is the turbine inlet temperature, which is given as 1,400. Right, 1,400. So T total 4 is 1,400. T total 3 we have calculated just now, 587. Fuel heating value we have 42,700. Okay, so since we have this one QR 42,700, so it's better Cp you change into kilojoule as well. So 1.005, because this one is in kilojoule, so Cp must be in the same unit. And T not 4, T total 4, 1,400. So we can calculate this one, F. Okay, so we have F around 0.0198 or 0.02. Okay, so remember I said the mass flow rate of the fuel is actually very small compared to the mass flow rate of the air. So here we can see from the fuel to air ratio, okay, the ratio is only 0.019, which is quite small, okay? But we still calculate it, we still use it, okay? We cannot neglect it. So 0.0198 so we have achieved this answer, okay? Okay, so next, velocity of the exhaust gas means the V7. Okay, so V7, so we have to continue. Okay, V7. So we have to continue this one. Calculate TO5, the exit temperature of after the turbine, exit temperature of the turbine. 0.5, okay, because 0.4 is completed. We know the that pressure, total pressure at 4 is the same as pressure 3, and TO4 is TIT, temperature. So now we proceed with 0.5. So for 0.5, we will use this one. Tak nampak ke tak? This one, okay? Bukan yang bawah ni. Not atas ni pun dah cukup. Okay? This above one pun dah cukup. Sebab because we have CP, we have T total 3, T total 2. Okay, lambda, if it's not given, then we assume it is 1. Okay? Lambda is actually, okay, the range ni. Okay. Lambda is the ratio of the power needed. Okay? Means that normally the power produced by the turbine, okay, lambda is actually the ratio of the power produced by the turbine over the power consumed by the compressor. Okay, means that if you produce 100% of the power from the turbine, we produce 100% power, but actually in real case, not all the power produced by the turbine is used or can be used by the compressor. Okay, because compressor need power, right, to run. Okay, but not all the power is 100% of the power produced by the turbine is used back by the compressor. Okay, there is always loss of heat, loss of energy. Okay, but in this case, ideal case, we assume that all the power produced by the turbine is used back to run the compressor. So 100% use. But actually in real case, it's stated here is usually around 75% to 85%. Okay, the rest is being rejected or is being wasted, be lost. Okay, the power loss, energy loss. Okay, but here is 100% use, so we assume lambda is 1. 100%, 100% 1. Okay, so lambda is 1. 1 plus F, the fuel to air ratio that we have calculated just now, 0.019A or 0.02. CP we have, TO4 we have, so we can calculate TO5. Okay, so we use this one. Okay, so this is the same. This is like the energy balance. Energy balance, not energy balance. Okay, it's the ratio. Okay, the power produced by the turbine and the power consumed used to run the compressor. Okay, so that from this definition, okay, W power. So we calculate the CPT, etc. Okay. Okay, try to calculate TO5. Okay, by using that equation. Okay. Sekejap Saya, ada yang nak masuk. Kita akan try to calculate TO5 nak tengok anak kelas online je. Okay. Calculate that first, okay? Okay. Okay, I'm back. TO5, okay? TO5. Okay. So we use this one, equation. So I rearrange directly the equation. So we have TO5, which is equals to TO4 minus TO3 minus TO2 over 1 plus F. Okay, so I've eliminated the CP. Okay, CP left and right, so we can eliminate the CP. CP is the same. Lambda is equal to 1. So we have this equation, okay? TO5 equals to TO4 minus TO3 minus TO2 total over 1 plus F. Okay, so TO5 is 1100, 1106. 1106 Kelvin. Okay, 1106 Kelvin. TO5. And then, okay, this one TO5. Okay, so there is no afterburner, okay? It's not stated in here with the afterburner for afterburner. So we assume 0.5 and 0.6 is the same. Okay, 0.5 and 0.6 is the same. Okay, no afterburner. So 0.5 and 0.6 is the same. So means that we have T5, T total 5 equals to T total 6. So this one is equal to T total 6. Okay? Okay. So what do we want to calculate exhaust speed V7. Okay, so this is TO5. Okay, next PO5, the pressure. So PO5, we will use the same isentropic equation for ideal gas. Okay, this time is for expansion, so is opposite. Okay, this one. Okay, this equation. This one, this one below. So this is the ideal gas isentropic equation. So the same. So TO5 over TO4 equals to PO, because expansion is opposite of the compression. So we can use this one. P total 5 over P total 4. Gamma minus 1 over gamma. Okay. So the same gamma, we use the same gamma. Otherwise, if it's given like the CP just now, because sometimes the exit from the combustion chamber, the CP and the gamma change because now we have added fuel. But here, for ideal case, we assume that specific heat and gamma stay the same. Okay. So gamma still 1.4. So here we want to calculate PO5. Okay? PO5. So we use this isentropic equation because isentropic yeah. Okay. So TO5 at PO5 pressure is 317. PO5 317.86 Kelvin. Kilopascal. Okay, which is also equals to PO6. Okay, because the 0.5 and 6 is the same. Here, this one. Okay, in this case. So 317.86 kilopascal equals to P total 6. Okay. So we have completed 0.5 and 6. Okay, we have completed 0.5 and 6. Now we move to the last point, 0.7, exit nozzle. Okay. So exit nozzle, okay, 0.6 is equal to 0.5. Otherwise, if you have the afterburner, if not, we won't use this equation. Okay, this part. No. This part is for afterburner as well, so skip. T total 6. Okay, tak apa, dia tak bagi sini. Okay, to calculate T total 6, so we use the same isentropic equation, because nozzle is actually kind of the same as turbine. Okay, that's why in the thermodynamic cycle, I mean the function, thermodynamic cycle decrease the temperature and pressure, and here 6 to 7 or 5 to 7 also the temperature and pressure decreasing. So we can use the same equation as for turbine. So temperature. So T total 6 over T7, okay, equals to P6, P7, okay. No, okay. So gamma minus 1 over gamma, okay. Okay, so here PO6 we already have, just now PO6 317. P7, okay, P7 is given, okay, P7 here, okay, it is unchoked nozzle, okay, remember unchoked nozzle. So unchoked nozzle, we assume that the exit pressure, which is P7, exit pressure is the same as the ambient pressure. So ambient pressure is 32 kilopascal, kan? So this one is 32 kilopascal. This one just now is 317, 317.86 kilopascal. P7 is the exit pressure. Exit pressure equals to ambient pressure because unchoked nozzle. And then T total 6 just now is 1106, 1106 Kelvin, which is equals to TO5. So we can calculate this one, T7. Okay, so T7, temperature exit of the nozzle is 563.6 Kelvin. Okay, around that, 563. Kita skip the okay, tak apa. Okay, T7 563.6 Kelvin. Okay, I hope you can follow the steps. Maybe you don't have enough time to calculate, but at least you understand the process and the steps. Okay. 563, T7, we use the normal isentropic ideal gas equation for nozzle. Okay, now last one, V7. So for V7, later on you can go back and see this video. Okay, so V7 or V of the exit. Okay, we use from this definition just now, 2CP. Okay, remember 2CP and just now total value. This is static value plus total value. Static value plus dynamic value equals to total value, right? So we use this definition to calculate V7. Okay, total plus static plus dynamic. So we have V7 equals to 2CP. Okay, T total 6 minus T7 square root. Okay, because power of 2 just now. So square root 2CP T06 minus T7. It's actually the same as equation as this one. Except that this one, if you don't have the value of T7, then we use pressure. Okay. Okay, so this one, okay. So T7 we have calculated before. We have T total 6, 2CP square root. So we have V7 1044.0 34 meter per second. So this is the velocity of the air, of the fluid exiting the nozzle. Okay, V7. V7 1044.34. By using the definition of total equals to static plus dynamic temperature. Okay. Okay, so exhaust speed, velocity of the exhaust gas. Okay, we have achieved this one. Next is air mass flow rate. Okay, air mass flow rate. Saya tak tunjuk ni. Okay, this one. Okay, we have calculated the B, question B, velocity of the exhaust gas. Now we want to calculate the air mass flow rate. Okay, so air mass flow rate, we will use the thrust equation because we have the thrust value 12.12 kilonewton. Okay. Okay, we use the thrust equation, this one. This is the thrust equation. Without the pressure, because pressure PE is equal to PA, unchoked nozzle. So we have MA. Okay, we want to calculate MA equals to T thrust force over 1 plus F VE, V7 minus V, the flight speed, the cruising flight speed just now. Okay. Okay, thrust. This is from the thrust equation, this one. Okay, so we want to calculate air mass flow rate. So we have 16.06 kilogram per second. Okay, this is 12.12. 12.12 kilonewton just now. So times 1000 kilo. Okay, don't forget to change into Newton. This equation you have to change into Newton. Don't use kilonewton because this is in SI units. So 1 plus F, V7 is 1044 just now. VF is the 310 cruising speed. So we get the mass flow rate, 16.06 kilogram per second. Okay, last one, the overall efficiency. Overall efficiency. So overall efficiency. Okay, so efficiency is in the chapter 2. Overall efficiency, chapter 2. Chapter 2, overall efficiency. So we use the simplified one. Propulsive efficiency, 2V over V plus V 7. Here, this one, this is VF, this is V7. So 2VF or the air speed, VF plus V7 exit. Okay. So we have 45.79%. Okay, 45.79%. Okay, VF, 310, and this one is 1000 just now, 1044. So the propulsive efficiency is 45.79. And the thermal efficiency, okay, this is T thrust times VF plus 1 over 2 or 0.5 M of the jet, okay, exit, ME. V7 minus VF square over MFQR. We can calculate MF from the fuel to air ratio. Fuel to air ratio times MA, so we get MF. So this is the thermal efficiency equation in chapter 2. So thermal efficiency is 60.36%. Okay. So in the end, overall efficiency is propulsive multiply thermal. So you get, so we have to get atas. So and propulsive multiply thermal. So we have 27, the overall efficiency, 27.75%. Okay. Okay. Saya cepat sikit tapi. Faham? Okay. I hope you guys understand. So propulsive efficiency, in order to calculate overall efficiency, we calculate first the propulsive efficiency using the simplified equation. Okay, ideal case. So we have 45.79%. And then we calculate thermal efficiency. Thermal efficiency, we have 60.36%. And we multiply both of them. So we get the overall efficiency 27.75%. 27.75% for overall efficiency. Okay, so we finish exercise 1. Memang dia panjang sikit. Okay, it takes a bit of time. Okay, so everyone okay? Cepat sangat ke?
Okay, doktor.
Ya ke? Boleh hadam ke? Nanti tengok balik.
InsyaAllah boleh, doktor.
Okay. Okay. This is question number 2. Okay, so the steps are a bit the same. Okay, single spool turbojet, flight Mach number. So this time we have Mach number, ambient condition, compressor pressure ratio, maximum temperature, which is maximum temperature is the turbine inlet temperature. Okay, the T4, 1300 Kelvin. Fuel heating value this time is 45,000. Exhaust nozzle area. Okay, means we have to calculate for we have to use the exhaust nozzle area if the nozzle is choked. Means that PA is not equal to PE. Okay, so we have to calculate the pressure thrust. So all the process are assumed ideal and no pressure is lost either in the combustion chamber or in the inoperative afterburner. So there is no afterburner. It means the afterburner is not functioning. Okay. So deduce that the nozzle is choked. Okay. Calculate the thrust force. Calculate the thrust force if the nozzle is unchoked. So there is two cases, unchoked and unchoked. So but first round we consider is as choked. Means PE is not equals to PA. So in order to deduce, to show, to prove that the nozzle is choked, okay, we have to prove this by calculating the critical pressure. Okay, so we will see whether the critical pressure is higher or lower than the ambient pressure. Okay, so in order to do that, the critical pressure is actually at the exit pressure, which is P7 at 0.7 exhaust nozzle. So, like I've mentioned, we have to start from the initial point. Point A, ambient, and the point 2, point 3, point 4, point 5, point 6, 7, until we have point 7, in order just to answer the first one. Okay, so the critical part, I mean not the critical part, the longest part is actually the first question usually, because you have to start from the initial. So once you get all the points, all the physical temperature, pressure at all those points, and then to calculate thrust force, etc., it's already is easier because you already have all those values, parameters. Okay, so just to answer whether the nozzle is choked or not, we have to start from the initial point. Okay, just like just now. Okay, now but I think I will skip certain steps because the steps is the same, okay, as the previous questions exercise. So you try to do by yourself, but I will give the answer. Okay. Okay, try to digest first. Okay. So, okay, so this time around we have Mach number, okay? Just now, question exercise 1, we have the cruising or flight speed, airspeed. This time we have Mach number. So, it is opposite or in other situation. We calculate the VF or just write is V, okay? So, we use the Mach number given, Mach number, gamma RT, ambient, okay? Okay, Mach number square root gamma RT, ambient. So we have 179 or 180 meter per second. Okay, the flight speed or cruising speed or the air speed, okay, V. Okay, this time we calculate the V by using the Mach number. Okay, then for diffuser 0.2, okay, diffuser 0.2, so we use, okay, so now we can use like in the slides here. So we use this equation, okay, because this time around we have Mach number, so we can use this one. No need to calculate the dynamic static temperature like just now because we have Mach number. Okay, so we can use this one. So use this equation, gamma 1.4, TA given, and this one also the same PA. And then we have the PO2. Okay, 238 Kelvin, PO2, 31.88. 31.88 kilopascal. Okay, by using this equation, both of this equation. Okay, then next, compressor, easier. We have what we want to calculate first. Temperature, okay. Calculate the temperature first. So we have the compressor pressure ratio 6 lah, 6 jadi. Compressor pressure ratio 6, okay. So we can use this one and this one. So this one is pi, 6, okay, 6. So TO3 397, 397.3 Kelvin. PO3 191.33. Okay, later on you verify the answers. I just show you the steps. Okay, so so this equation using the compressor pressure ratio 6. Okay, so we have 0.3 and then 0.4. 0.4. Okay, 0.4. So 0.4, TO4 is 1300 Kelvin, the maximum temperature. Maximum temperature. Okay, so TO4 1300 Kelvin maximum temperature because the afterburner is not functioning in operative, so the maximum temperature will be the turbine in the temperature, which is TO4. And PO4, okay, ideal case, so PO4 equals to PO3, no pressure loss, constant pressure during the combustion chamber, combustion process. So PO3 just now 191, 191.33 kilopascal. Okay, so 0.4 settle. 0.5, okay? But in order to calculate 0.5, we have to calculate the fuel to air ratio first. Okay? So using the equation, the same equation, this one, fuel to air ratio. Okay? Okay, CP 1005 or 1.0005. TO4 1300, TO3 397 just now. QR, the fuel time value 45,000. Okay, so we can calculate this F. So F is 0.02 also. 0.02009. Okay. 0.0209 or 0.02. Okay. So you can see here in your test or your final exam or whatever or your homework, if you we see here that the fuel to air ratio is around 0.0 something. Okay, until 2 decimal point. So if you calculate by yourself in test or exam, etc., if you found the value is a bit a bit strange or different, cannot in the same approximate value that we usually do, okay, that we usually achieve in tutorial, so means that there is something wrong with your calculation. So we can verify with that. Okay, the fuel to air ratio must be logic. Okay, it's quite small. Okay, lagi. Okay, next T.5. Okay, this time around, for exercise 2, actually lambda, I didn't write it here, but actually lambda is given, means that the lambda mean the power produced by turbine is not 100% used by the compressor. So lambda here is 80%, 0.8. Okay, lambda is 80%, 0.8. Okay, so we have to use this one to calculate 0.5. So 0.5. So the same step just now, 0.5, this one, use this one. Same steps. So we have T5. Okay, same equation, 1105 Kelvin. And PO5 also, we use this one, the isentropic equation. PO5 is 182.63 kilopascal. Okay, the same process as exercise 1. Okay, I repeat. We have TO4 and 1300, the maximum temperature throughout the engine. PO4 is equals to PO3 because ideal case, no pressure loss, 191.33. Fuel to air ratio around 0.02. Lambda 0.8 given. PO5, okay, 1105 Kelvin. And PO5 using the isentropic ideal gas equation, 182.63 kilopascal. Okay. And then 0.6. 0.6 is the same, no afterburner, so 0.6 is the same as 0.5. And last one, 0.7. Okay, we want to deduce that the nozzle is choked. Okay, nozzle is choked. Yeah. Okay. So check if the nozzle is choked. So we use explain. Okay, this one. Dia tak equation sekejap. Operative afterburner. Okay. Okay. I missed one page actually, one page of the question, but it's okay. I'll write this here. So you have PO6, okay, over PC. PC is the critical point. We want to search for the critical point in order to deduce that the nozzle is choked or unchoked. So P total 6 over PC equals to gamma plus 1 over 2 gamma minus 1. Okay? This equation is actually comes from the same equation as this one, okay? The first equation, okay, this one, the general equation in the diffuser or in the nozzle, this one, right? When a critical point, remember critical point is when the Mach number is equal to 1. Okay? So if we pressure, this one pressure. So imagine this is the general equation for nozzle or diffuser, right? So Mach number is equal to 1. So if the Mach number equal to 1, we will get this equation. Okay? Just rearrange it. Okay? So PA, it's like PC goes to this left hand side and Mach number equals to 1. So rearrange, we have this equation. Gamma plus 1 over 2, gamma over gamma, power of gamma over gamma minus 1. Okay, this is where how this equation derived from. Okay, so we have this one at critical point, only at critical point, because critical point Mach number equals to 1. Okay, so we want to search for PC, critical pressure, to prove that the nozzle is choked. Okay, so PO6 just now, we have calculated previously, PO6 is equal to PO5, which is 182 just now, 182.63 kilopascal. Gamma 1.4 here we use. Okay, so we have PC. So PC is 96.48 kilopascal. 96.48 kilopascal. Okay, I hope you understand where does this come from. Okay, it's actually there is no new equation or new formula. It actually comes from the fundamental equation that I have learned in thermodynamics. Okay, this equations actually come from the definition of the total values static plus dynamic. So I've explained just now. So we arrange, include the Mach number, etc. So we have this equation. And from this one here, if the Mach number is equal to 1, then we have this equation. So it's actually the same. Okay. Okay. PC critical pressure is 96.48, which is if we compare with the ambient pressure is now given, ambient pressure is 25 kilopascal, PA 25 kilopascal, right? Okay. So if we compare here, we see that the critical pressure is higher, PC is higher than PA, ambient, right? Okay, PC is higher than PA. Then thus, this means that the nozzle is choked. Nozzle is choked or limited. The air is limited, right? I said just now. Choke limited. Not the nozzle limited. Nozzle is choked, but the air, the fluid inside the nozzle is limited. Okay? Until up to the point of the critical point. Okay? So PC higher than PA, we have proved that PC critical pressure is higher than the ambient pressure, so the nozzle is choked. Okay, so we have answered the first questions. All right, nozzle is choked, critical point, because the critical pressure is higher than the ambient pressure. Okay, okay everyone. Okay, next is calculate the thrust force. Okay, so we have all we by looking at the thrust equation, we have all the value. We have MA not yet. we have F, 1 plus F. So we want to calculate the thrust force. Okay, so F we have VE, V7, not yet. Okay, V we have initial, PE is the pre-critical. Okay, PA ambient, and AE is given. Okay, so we want to use this one. We want to calculate thrust force. So we need to calculate mass flow rate first and V7, VE, exit pressure. Okay. So if the nozzle is choked, okay, nozzle is choked and the critical pressure is higher than the ambient pressure just now. If the nozzle is choked, then we assume that P7, in this case, P7 is equal to the critical pressure for the for choke nozzle. Choke nozzle, P7 is equal to critical pressure, which is just now 96.48 or 96.5 kilopascal. Okay. Okay. So okay, so P7 we have, so T7 is TC also, which is equals to T total 6 over gamma plus 1 over 2. This also, like the pressure equation just now, this also comes from the Mach number. This is also the same, derived from here. Okay, Mach number equals to 1. So we want to calculate TC, it's like a TA here. Okay, so we have total temperature. Now we want to calculate T6. Okay. Okay, so T7 or TC critical is 920.8 Kelvin, 920.8 Kelvin. And V7, which is because since the nozzle is choked and the pressure and temperature is the pressure and temperature at the critical point, so the exit nozzle, the speed of the exit nozzle, the velocity, the speed at the exit of the nozzle is actually the sonic speed. Okay, because Mach number equals to 1 kan? Mach number equals to 1, so actually the speed of the air inside the engine exit the nozzle achieve the sonic speed. So V7 in this case, choke nozzle, is gamma RT. Okay? No need to calculate with Mach number because Mach number is equal to 1. So we have 608.26 Kelvin. Okay, 608.26 Kelvin. Square root gamma RT. Okay, so we have V7. Last one. To calculate thrust force, we have to get the MA, mass flow rate. Okay, we have all these values already, except we don't have MA. Okay, MA.
V7 is in meter per seconds ke Kelvin?
Meter per second, sorry.
Okay.
Meter per second. Okay, thank you. 608 velocity. Okay, last one, mass flow rate MA. So MA, okay, MA. For MA, we use this one. Rho AV. A. Because we have the values of the area. Okay, at the exit. Row V7, A7. Row AV or row VA sama. Okay. Okay. The definition of the mass flow rate, density, velocity, area. We have the value of the area given. Okay. Now we have V7, we have A7, but the density. Okay, we cannot use directly with density 1000 though. Kita kena calculate, we have to calculate density. So to calculate density, we use the ideal gas. Okay, the ideal gas density is equals to P7 RT7. Ideal gas in thermodynamic Remember thermodynamic ideal gas ni kan? PV equals to RT, right? Remember this perfect gas equation, PV equals to RT. So V is the opposite of the density, P over rho, RT, right? So we want to calculate rho, this density, we use P over RT. Okay? Ideal gas, perfect gas equation, PV RT. So this one, density. Okay, so we have all this value, P7, and just now 96.48 kilopascal. Okay, change to Pascal. This one you have to use all the SI units. R is 287. T7 just now 920. B7, A7 given. Okay, so we have MA. MA equals to 44.41 kilogram per second. Okay, 44.41 kilogram per second. So lastly, we can solve the thrust force. Okay, thrust force using this equation. So we just substitute all the values in here. So the thrust force is around 33.914 kilonewton. 33.914 kilonewton. 33.9 or 34. 34,000 newton, 33.9 kilonewton. Okay. So this is the thrust force value. Okay. In the exercise, in the questions, last question, it asks you about if the nozzle is unchoked. Okay. We don't have to repeat from the initial point. It's just that we have to, starting from the point P7, okay, the critical point just now. This time around, we have to change. Just now, for choked nozzle, we assume that the P7 is equals to the critical pressure, right? But if the nozzle is unchoked, then the PE, exit pressure, or P7 is equals to the ambient pressure. Okay, back to the same as exercise 1. P7, PE equals to PA. So use back that definition to calculate T7, V7, right? So the same equation as exercise 1. Okay, because unchoked. Just calculate back starting from P7, not from the initial point. Starting from just from the P7, calculate back, but using the equation from exercise 1 just now, because this time is unchoked. So for the case of unchoked, nanti korang calculate later on. Unchoked nozzle P7 will be equals to PA. Okay, so PA 25 kilopascal. Okay, so you calculate T7. Okay, using the isentropic equation, ideal gas equation tu, 625 Kelvin, 625 Kelvin, and then you calculate V7. Okay, the same equation as just exercise 1, 2CP square root, etc. So you have 983.96 meter per second. And that's it. Okay. You have this P7, T7, V7, and then you calculate transpose. So this time around, transpose will be easier because you don't need the second term, the pressure thrust. Okay, because PE equals to PA, so you don't need that one. You just use the first term, MA 1 plus FV7 minus V. Okay, so you have transpose 36.65 kilo Newton. 36.65 kilonewton. Okay? Okay, so unchoked nozzle, the transpose is higher than the choked nozzle, okay? Unchoked is like the ideal case, okay? Okay, so that's it. 36.65 kilonewton for unchoked. Number 3. Okay, so we have finished both of the tutorials. You at least you understand the steps, okay? The process, why we use this equation and then why this equation next, okay? Otherwise, the calculation you can do by yourself, by your own self, okay? You just calculate. But you at least you understand where does this equation come from, okay? So because I want to relate, try to relate all these thermodynamic equation of the cycles is actually not a new formula for you. Okay, it's actually come from your what you have learned in aerothermodynamic last year, previous semester. Okay, so we just use back the isotropic equation, TS diagram, all of that you have learned in aerothermodynamics. So it's not a new formula, a new principle, or a new law. Okay. So if you understand, revise back, okay, your thermodynamic class, okay. So the PV equals to RT just now, the ideal gas equation, okay. So T transpose. Okay, so last, okay, this one is for your homework. So it accounted for 10%. To cover a bit your assignment, so assignment 30%, but assignment at the end of the semester, and for you also to so that you can try to do by your own self, try to understand clearly in detail before we do test, okay, after Raya, after semester break. So try to do this first so that you already familiarized with the process, okay. So it's actually, this equation is actually direct equation. It's just that different. This time is turbofan. We haven't done example concerning turbofan. Okay, we have only done example concerning turbojet. Okay, but the questions, this exercise is actually direct. Okay, you just have to calculate the TSFC, the thrust per unit mass flow rate, and the TSFC, and all the values, the parameters is given. It's just that you have to correctly apply, know where to apply which equation. Okay, I just want you to practice that. Otherwise, this question is direct. There is no hidden value or hidden things, etc. So it is direct. Just calculate. Okay, just that I want you to practice to apply the equation and to understand the process, the thermodynamic cycle. Okay. So I think you can do this, okay, with the equations already given in the slides or in the reference book, any reference book that you have, okay. So that's it from me. So this one, okay, submission. We are in 6 May. Next week Raya, next 2 weeks test. The same day as test, right? Means it's okay if you want to submit after. Okay, we have test on the 20th, 20 May, right? After Raya, the week 8, 20 May. So submit this homework on the same day. Whether before or after the test is okay. Just on the same day. Okay? So submission. So that I want to make sure that you do this homework while while doing your revision for test. Okay, it is for your own good. Okay, submission homework. 20 Mei the same day as test. So whether before or after the test you want to submit is okay. 20. Okay, nak tu je. So test, we will do test, online test, just like the numerical test. So I will do Google Form, and we have around 1.5 hour. Okay, we start at 9:15 lah. 9:15 until 11 a.m. 9:15, 11 a.m. What else? So all the chapters that we have learned until now. The first one is just introduction to every engine, and then performance parameters and this chapter. Okay, turbojet. Okay, so I will ask about turbojet. I mean for this chapter turbojet engine, turbofan you do as homework. Okay. Okay, I think that's all. So I'll see you guys after Raya during the test. Okay, insyaAllah. Any questions? Oh, ni attendance, sorry. Let's stop the recording.